Okay, in this lecture video, transient signals on transmission line number 6, we will be talking about initially charged lines, or lines that start out charged, and then we're going to discuss the process of how they discharge. To this point, we've looked at what happens when we connect a battery and send positive or negative voltages back and forth along a transmission line in order to bring up the circuit to the steady state, as if the battery had always been connected. But we now need to consider basically the opposite, or the negative flip that we might expect on a digital circuit, and how the line actually restores discharging in a case like that. So this lecture is divided up into 3 pieces. The first, we're going to talk about what it means for a transmission line to be in steady state. And then we're going to dive into the specifics of how we treat a discharging line, or a negative going voltage, or a voltage that disconnects, or any other change like that, since this will be more general. And then in part 3, we will go over a numerical example. Okay, so let me go back to our traditional picture of a transmission line. We've been considering a problem that looks like this. Right, we have a generator voltage VG connected to an internal resistance RG. These cannot be decoupled from each other. The resistance is part of the generator, even though I draw them separately. And then these connect to a transmission line, which I draw with 2 tubes like this. This transmission line has an intrinsic impedance Z0, and at the end, it's terminated with some resistor, which we're going to designate as RL. This resistor could be the input to a logic gate, or a transistor, or an op amp, or whatever circuit is next, beyond the transmission line after some trace or some cabling. Now, if we wait long enough, we know that the transmission line circuit should eventually settle out to the same place that it would have if there were no transmission lines. Coming into this class, you would have simply replaced this transmission line with 2 wires. This would have been a very simple analysis where you take the voltage VG and do a resistor divider between RG and RL. The current would just be VG divided by the sum of those resistances, and it would be pretty simple. Right now, we have this complication with this transmission line in between that has to ping pong information back and forth. But if we wait long enough, right, remember, we're treating this as there is a switch that closes at t = 0 to connect that voltage to the rest of the line. And if we wait long enough, right, as t goes toward infinity, we're going to simply remove the transmission line and replace it with 2 simple wires. And we've got VG connected to RG and RL. Right, after a while, the whole circuit will approach what we would call a lumped system anyways, where everything is just mushed into one point. Again, after some amount of time has passed, enough time for those back and forth ping pongs to settle out. Now, if we think about this, there is, now that we've spent all this time deriving what happens in a transmission line, we seem to have a bit of a conflict here, because we've talked about how the transmission line forces a certain ratio of voltage to current, right? That the positive going wave divided by the negative going current in that wave must equal Z0, right? And so if Z0 and RL are different, and we know that after a while, right, IL, the current on the load, is just going to be equal to VG divided by RL plus RG, then we know that there's going to be a mismatch, because RL is not the same as Z0. So we think about steady state, and we say, okay, there's a voltage and current on RL, which is no longer has the same ratio as the voltage and current on the transmission line. Something's wrong, right? Because we said that the transmission line forces a certain impedance, and the load resistor forces a certain impedance. So how could it be that these 2 things coexist after a very long time? What is the steady state condition? So how do we rectify those things? And so the only way we can rectify this is by saying that at steady state, we actually have the sum of 2 waves. There is a positive going wave, right, which we're going to call V positive with an associated current I positive. And there's also a negative going wave, which I'm going to denote as V negative, that has an associated current I negative. If we consider this as having two waves going in positive and negative directions, and we treat the sum of those two waves as being what's actually present on the transmission line, then we can simultaneously rectify the requirement of the load to have a certain voltage to current ratio and the requirement of the transmission line to have a certain voltage to current ratio. Okay, so let's take a look at this from a different perspective, and let's consider how this transmission line would charge up and reach steady state. All right, and let's look at this from the perspective of both voltage and current. So I'm going to draw a bounce diagram for a generic transmission line that has a resistor on one end, and the moment that we first connect t equals 0 will be the first moment that we connect the generator to the source. And what's going to happen is we're just going to have these zigzagging waves. It's going to go back and forth, back and forth, okay, onwards. So we'll just keep going. And that initial voltage, let's call that VA, will be moving this way. And we also have a current, IA, also moving this way. And we know from the transmission line impedance that VA divided by IA must equal Z0. Okay, now at that first reflection, right, VA is going to reflect off of the load, and it's going to be moving back the other way. Let's call VB to be that reflected, the reflected wave, right? And I'm going to say IB is the current of that wave that's going in the other direction, right? The same relationship still holds as before, that VB divided by IB equals Z0. You might get another reflection again, in which case we have a VC and there's an associated current with it, IC, and same relationship for that, VC divided by IC equals Z0, and this will just continue onwards. So here's the question I want to ask you. All right, let me just draw one more line in here. Right, this will be VD and VE, VD, VE, and I'll draw the currents as well. ID and IE. Okay, so let me ask you this question. I'm going to draw a green dot right here. I'm going to ask you the question, what is the voltage at this green dot? Meaning the voltage in the middle of this transmission line at this particular point in time, right? What's the voltage and what is the current? I asked you that simple question. In order to figure out what the total voltage is, we're going to look at all the waves that pass by. So we start out with the voltage of 0, right? So here, the voltage everywhere inside here, let's do that in a different color. Right? The voltage everywhere inside this little shaded section has a voltage of 0. Once this wave passes by, it elevates the voltage of the transmission line to the value of V equals A. So everywhere within this triangle right here, sorry, that's not VA equals 0. That's has a voltage of V equals VA, because that VA wave has swept by and elevated everything. All right, let's repeat this again. The voltage right here, V, will equal to VA plus VB, because the second wave, VB, has swept by, and it adds on top of the wave that existed before. So the voltage everywhere in here is just going to be VA plus VB. Moving on, the voltage right here will be just the sum of all the waves that have swept by. Right? So V equals VA plus VB plus VC plus VD, just the sum of all those, plus VB. However, what's the current right there? Right? Next question is, what is the current in this location? The current is a little bit different, because if I look at IA and I look at IB, they are traveling in opposite directions from each other, which means they actually cancel each other out, right? If IA and IB are equal, then the sum current, the sum total of that is 0. So the way I represent that is I'm going to have an IA, but I have to subtract IB because IB is moving in the opposite direction. Then I'm going to add IC because it's positive going. I'm going to subtract ID, and then I'm going to add IE. Okay? So at this location right here, we've got a total voltage where we just sum up the voltages of all the waves that go by. And we have a total current where we sum up the same voltages. Excuse me. We sum up the same currents, except we have to add a negative sign to the negative going waves. Then the total voltage at this location will just be the sum of those. So what's the V total divided by I total is not necessarily going to be the same as Z0. It will not be the same as the transmission line impedance because of these negative signs we have to throw on the currents that we didn't throw on the voltage. Right? I can rewrite this current equation as follows: I equals VA over Z0 minus VB over Z0 plus VC over Z0 minus VD over Z0 plus VE over Z0. Right? The ratio of V to I is no longer going to be the same as Z0, right? At least not in general. So we have a situation where at a given spot on the transmission line, the voltage to current ratio in sum total of everything is no longer the same as the transmission line impedance, even though all the individual waves that are sweeping by still have that same voltage to current ratio. And that's the key to understanding what happens to initially charged transmission lines. All right, so the one thing I want to recap is this voltage VA, as it sweeps by, it basically never stops. It's a wall of water that's moving along, with a certain height, let's say 2 inches high. It sweeps by. The water is always coming because that generator is still on. So that VA stays there effectively permanently until we make some other change. VB builds on top of it, and VC builds on top of that. So we have to add up all of these effects together in order to determine what the voltage is right here. And so the steady state condition is the sum of every single wave that has swept by in the positive or negative direction until we have reached steady state. So after a very long time, if we extrapolate this all the way down to t equals infinity, eventually we're going to have two waves that result, right? There's going to be what we're going to call V positive, which is a sum of all the voltages that have moved in the positive direction, all built on top of each other, right? It's the sum of all the positive going voltages. And we're also going to have the negative, which is equal to the sum of the negative going voltages. And for each one V positive and V negative, we can guarantee that V positive over I positive equals Z0. And we can guarantee that V negative over I negative equals Z0. So individually for the waves that are resulting, we have this transmission line impedance obeyed, but the sum total of the two is not necessarily obeyed. All right, so let me just try to visualize this with another quick simulation, just a second. I have to open this beforehand. All right, so I'm going to set a generator impedance of 50 ohms. I'm going to set a line impedance of 100 ohms. I'm going to set a load impedance of 200 ohms. All right, I'm going to press go, and I'm going to let this settle out. Here comes the wave. It's 2/3 of a volt propagating in the positive direction. It reflects with a positive coefficient off of the load. And let me just stop right here for a second. Now, at this moment, we have a negative going wave that has a pretty small value to it, but it's built on top of the positive going wave that's still going, right? This is water that's going through a pipe or a wave that's sweeping along the floor, and the water's still coming. So anything that goes in the other direction builds on top of it. And that process is going to keep on going. We're going to keep getting wave built on top of wave built on top of wave. Now, bear in mind, waves can be negative, right? So waves can reflect with a negative coefficient, which would basically remove voltages, but that's still built on top of whatever was there. So after a very long time, we've got this voltage to current ratio, which is not the same as E0 if we look at the net total. And to show you that, I want to click on this little current bar right here. And let me simulate this and stop it. So if I click on the current, it's now plotting the current and voltage at the same time. Now you can't see it because right now they're superimposed on top of each other, but the voltage is basically a darker red and the current is more like an orangish red. And the tick marks here are going to be normalized by Z0. So take the current and multiply it by Z0, and that's what's displayed. So because the voltage and the current have the same ratio of Z0, then when you multiply the current by Z0, they plot right on top of each other. So here they go, right? When this reaches the end of the transmission line, we're going to get a positive reflection coefficient for the voltage, but a negative reflection coefficient for the current. Why? Because the water level, which is basically voltage, builds on top, right? We got 1 volt coming in, we got a reflection of 1/2, and that builds on top. And so in total, we get the sum of those. The current works in the other way. If I've got water flowing this way, and I've got water flowing the other way, those two flows cancel each other out in terms of like the net flow of water. So the moment this reflection occurs, you'll see that the voltage and the current are diverging from each other, right? They're no longer the same. Even though the positive going and negative going wave have the same voltage to current ratio, the sum total of them is not Z0. So I'm just gonna let this simulation play out, and you'll see that it's basically going to settle out. And when we talk about steady state conditions on transmission line, this is what we're talking about. That at the end of the day, after all these waves sweep by, there's a single positive going wave and a single negative going wave, each of which obeys the transmission line impedance, but the sum total of which yields a different ratio of V to I. So let me try to visualize this for you a different way, right? And what it means for there to be steady state. And I'm going to go back to this idea of kind of like water flowing in pipes. And let's say that the whole circuit is basically a big loop, okay? On one end of the loop, we are pumping in voltage, right? This is where our generator is. Hang on a second, put that back. This is basically where the source is, and we're pumping in waves. So this is the input voltage that's being shoved into the transmission line. That V in will be equal to the transmission line impedance divided by Z0 plus RG times our generator voltage, right? That's that first voltage that we put in at the very beginning. Take our generator voltage and apply a resistor divider with the transmission line impedance. That's what this V in represents, right? That's what's being shoved into the transmission line. And then once it goes in, we're going to have a reflection, right? There's a reflection right here, right, where there is gamma L. We know what gamma L is. Gamma L equals our load resistance minus our transmission line impedance divided by the sum. And we've also got a reflection at the generator, gamma G, and gamma G equals our generator resistance minus Z0 divided by the sum. All right, and we're also going to have some dissipated power that's wasted right here. Right, so here is dissipated power. This is the current that's flowing through the generator resistor that's wasted. And there's also some power that flows through the load resistor that's wasted, right? And that's dissipated power, or it may not be wasted, but let's say it's no longer in the circuit. All right. So in the end of this, there's going to be a positive going voltage here, V positive, and a negative going voltage, V negative. And we can basically come up with relationships for how V positive and V negative relate to each other, right? And we have a couple of, we have some knowledge of how they relate to each other. We know, for example, that V negative must equal to our load reflection coefficient times V positive, right? That is well known. Every time V positive comes in, it reflects and makes V negative. So even if V positive consists of many waves superimposed, the sum total, each one reflects off the reflection coefficient. So this all scales. We also know that V positive will be equal to the negative going voltage multiplied by gamma G, right? We've got the negative voltage that reflects and becomes V positive, but we have to add our V into it, right? So these are basically our two waves, our two equations that help us figure out what are V positive and what are V negative. If you substitute the equations for gamma L, gamma G, and V in, and solve all that, then you can basically figure out what are V positive and V negative, right? What is the steady state positive going voltage and the steady state negative going voltage? And it works out to be the following, and this is probably something that's worth memorizing. V positive equals VL plus IL Z0 divided by 2, and V negative equals VL minus IL Z0 over 2. All right, here's the first one. Right, so remember, V positive is the sum of every single positive going wave that comes through if we wait long enough for the circuit to reach steady state. Add all those voltages together, the positive going voltages, and it's going to end up being V positive. Same for V negative. Take all the negative going voltages, extend out to t equals infinity, and they're going to sum up to V negative. All right. Now you can trust me, or you can verify it if you'd like. There's a couple sanity checks that we can apply to make sure this is right. We'll try to get to those later. But let me just firstly remind you that VL and IL are the steady state voltages and currents on the load. So what that means is, pretend there's no transmission line. Pretend you just have battery connected to generator resistance, connected to load resistor, right? Go out and figure out what is the voltage and current on the load in this case. That's just a straightforward resistor divider. And take the current is VG divided by the sum of those two resistances. That's what VL and IL are. Right, so substitute those in here. Now, if you want proof that this equation is correct, I would encourage you to try out the matched condition. Right, the matched condition is if the load matches the line. Right, so let's try this out. So if RL equals Z0, plug that into this, and you can verify. I'll leave this as an exercise to be done later. But if you plug in RL equals Z0, you can verify that V negative equals 0. Right? Now that's very comforting, because we know that if the load has the same resistance as the impedance of the line, then the reflection coefficient is 0. Therefore, there should be no V negatives. There should never have been a negative going wave to begin with. And so this works out. You can demonstrate this yourself. And so that is one way to do a quick sanity check to make sure that what we've got makes sense. All right. There's a couple more sanity checks that are in the notes that you're welcome to look at. So understanding this is very important, because you have to understand the steady state as being a net positive going voltage and a net negative going voltage, because when we disrupt things, we're going to ask the question of what's going to change, and then we're going to treat the evolution of the circuit from that point. And that's what we're going to cover in the next video. We're going to learn to disrupt this steady state that we have now established.